Alrighty, good morning, ladies and gentlemen. Happy Monday. Today I'm going to go over a couple of notes. This should be the last thing you need to basically deal with any trigonometry problem we are going to deal with in this class. So today we are looking at something called 3D trigonometry or three-dimensional trigonometry. So we're looking at three-dimensional objects or representations of three-dimensional objects and figuring out side lengths of them. Now, this sounds like a big step up, but in reality, it's actually pretty similar to what we've been doing. Actually, it's exactly the same as what we've been doing, just with an added layer of difficulty of trying to interpret what the question is asking for. So there's a couple of problems distinct to 3D trig that I'll go over, and I'll show you what I mean, and we'll talk about it. So first up, problem number 1 is something about angles. So for example, we've been dealing with two-dimensional trig, so I have the triangle ABC right here. If I was to have this symbol here, it is pretty clear it is referring to angle A. So we use this little symbol. It looks like a less than symbol, but it's a little bit flatter on the bottom. And we use that to basically say angle A. And if we look for angle A, we look for the point A. Now, 2D space, this is easy to deal with, but you'll see a problem right here. Now if I go for angle A, which angle are they referring to? I see that the point A is right here, but if I notice, there is a line going up, a line going away, and a line going side to side. So the dotted line here represents going into the page, but behind something, so we can't actually see it. So we actually have three angles here. I have the angle that's shown by A to B to E, which would look sort of like A, E, B. So I'll use the sides that we know. We know that this is 5 centimeters, and we know that this is 9 centimeters, and I don't know what this is. Is it talking about this angle? Or is it talking about maybe AED? Or EAD? Sorry, I'll rewrite these a little bit. So EAD is actually part of this face, and it's a 90-degree angle, or is it referring to angle A or BAD, bad, which is part of the rectangle ABCD, and again it's 90 degrees, so it's the flat side. So you can see here I actually have three different angles to choose from, and if there was more points coming off of A, I would have even more things to pick from. But you can see right here, this is the complication. So I've given part of the solution. When we talk about angles in 3 dimensions, we use 3-letter angles. So what I'll say by that is if I wanted to say have this one, I would use angle EAB. And how I read this is starting from E, go to point A, and then to point B. So the way I can think about it is the middle letter is where my angle opens up from, and I'll say the edges of the angle go to these points. So this way I can talk about any point. If I was to write angle BAD. I would find the point B, I would go to my A, and then I would go to D. So my angle would be the point that is in between those. And from here, I can actually use all the same rules to solve for these problems. It's going to take some creative thinking, but I'll go through a few different problems. So the first one is calculate the angle between the line D and F and the plane ABCD in the cuboid. This is our rectangular prism. Pictured below, giving your answer to 1 decimal place. So first up, I need to figure out what they're asking for. So between the line D and F, so I'm looking for D and I'm looking for F, and they want the line. But there's no line currently. So what they're actually saying is, if I was to go through, basically cut through this box, go from corner to corner, that's the line that they're talking about here. And they want the angle with the plane A, B, C, and D. So the plane, if I look for A, B, C, and D, they're looking for this sort of the bottom side of the box. So they are looking for the angle, and to kind of round this off, I'm going to make myself a right triangle. And to do that, I notice I'm going from F to D, so I'm going from this line down, and then I'm making a triangle here. And I know it's a right triangle because this is a rectangular prism, so it is going to be like that. So I am looking at the triangle F, B, and D. The issue with this is I currently am looking for this angle here. I'll call it theta. The reason why I know I'm looking for it is because B to D, both B and D are on the bottom side of this box. So I know that this line that I've drawn here is touching the bottom of the box. So I know that, and I know if G to C is 10, I'll also know that F to B is 10 centimeters. But otherwise, I don't actually know either of these. So currently, I don't have enough to solve. This question is actually asking me to solve the angle BDF, but I need more info. So my step here is to look for a right triangle with a common or shared side. Now, the problem with this is it's a box. So there's not much I can look for here. And one of the ones I want to avoid is this line that's going through the middle. The reason why I'm saying to avoid it is because it kind of cuts through the middle of the box. It's not really close to any of the edges. So I want ones that line up with the edges decently. So what I'm actually going to pick, and you'll see why in a second, is A to B and A to D. And then if I notice, if I was to look at sort of what I have the bottom here, this is a bottom view. I have A, B, C, and D. I've already drawn B to D, and I notice that, oh hey, if I work with these lines here, I actually have a right triangle. And I know that B to A is 6 centimeters, and I know that A to D, I'm getting confused by this half, A to D is 5 centimeters. So now I can actually solve for this one. So one of the tricks is look for the right triangle with common sides, and I'll put on the face of the shape. so on the outside face. It's probably the best place to look. So F to D goes through the shape. It's not really connected to any of the faces. So try to avoid that if possible. So now I have the triangle. Oops, sorry. I have A, B, D, 6, 5. I'm looking for this one. I'll call it X. And just for a second, if I draw where the other triangle is, if I ignore the fact that it's in 3D space, I'm trying to solve for theta, which is right here. And I know that this is 10, so this very quickly just becomes a two-dimensional problem. And like, if I think about it, if I just flatten out this triangle, currently it's standing up and down, if I flatten it, it would make the same shape. I don't have to stretch it or skew it or anything like that. So my first step, I want to solve for x, and then I want to solve for my angle. So solving x, I have 6 squared plus 5 squared equals x squared. So again, I'm applying Pythagoras just like I did before. So from here, and you know what, I'll change x squared to bd squared, just so we know that this is this side that we're talking about. So following through, I get 36, I get 25, added them together. So this gives me 61 is equal to bd squared. So b times d would be equal to 7.81. So all I did there was I square rooted to get my b times d, or b to d. So then now I have the triangle with theta. This is 10, and I've solved for this side here, so it's 7.81. So again, I'm looking at my SOHCAHTOA, and I see that I have an opposite and I have an adjacent here. So I want to use my tan. So tan of theta is equal to opposite over adjacent. So I'm going to put an arrow. So I have tan of theta is equal to 10 over 7.81. And I like to do my stuff all in one step. I want to know what theta is. So my next step is to take inverse tan of both sides. So this is going to be inverse tan of 10 divided by 7.81. And this gives me a value of 52 degrees when I punch it into my calculator. So there's a first example. I've solved for an angle. What you basically need to do is to find two triangles and turn it into a 2D problem. So one of the things I want you to notice is that this is the same as a 2D problem where you have to set up your triangles. So it functions the same as a two-dimensional problem, but rather than me or whoever's asking giving you the problem already spelled out for you, you need to find a way to match sides. So for example, you could have gone about this a different way. I'm showing probably the most streamlined way possible. So what I mean by that is it would be possible to calculate, say, a triangle and then find a third triangle that matches up to one of the sides. Like maybe you could actually get this hypotenuse here and solve for it. But again, you're trying to save yourself steps whenever possible. So let's look at another problem. So they're now looking for calculate the angle between the line A to F. So the first thing I'm going to do is I'm going to draw a line. I'm going to find my A, I'm going to find my F, and I'm going to connect the two with a line. So it wants me to go across the face, and it's saying calculate the angle of the line between this line and the plane ABCD. So ABCD is this bottom box. So it wants me, if I draw a dotted line, I'm thinking of going from A to C because that's along this bottom box. And it wants this angle here. So the first step I want to do is make my triangle number 1. So it's going through the box somewhat. So I don't know what any of these sides are. If I look, or I know what one of them is. So if I draw A, C, and F, I've made my first right triangle. This one's 5 centimeters. This one, I don't know, and this one I don't know, because both of them cut across the face and don't use any of the other shapes. Now, this is where picking our triangle is going to be important, because if I look, what I've just drawn is actually half of sorry, I'm actually getting mixed up. What I see here is there's actually, if I look, my first thought is I see A, E, F, and D, and I notice that A to F to D makes this nice right triangle here. Now, the problem with that is it gives me one of the sides, but I don't know any angles, I don't know any side lengths. I actually don't think that's the best triangle. The reason being is even though it's a right triangle, even though I could make that, it doesn't give me any new information. It gives me this 3 centimeters, but to actually solve for A to F, I would need to calculate D to F. So I would have to make a third triangle. So I want to see if there's a triangle I can make without having to do that. And if I look towards my base, I notice I have on the bottom, I have a right triangle that goes A to C to D. I have 3 centimeters and 9 centimeters. And I notice that I have A to C on both of my triangles, so I can actually put them together, so I end up with sort of this A to F to C, and then I've got my D here. And I can solve for that. What I was saying before is if I had my AFC, I could connect and make another right triangle with D. So I have AFD, but then to calculate anything to go on there, I would need to make a third triangle that was F to D to C. So I'm making my job way more complicated than I have to. If you can, keep it simple. So I notice from here I can now solve, I'll call it A to C. So again, solving A to C, I have 3 squared plus 9 squared is equal to AC squared. And plugging in, this gives me a size of, well, this will give me 90 on this side. So A to C is equal to 9.49 centimeters. So I now can take that value and plug it in here. And from there, the angle I'm trying to solve for, I'll call it by its proper name, CAF. So is equal to theta, so that's what I'm trying to solve for. And now I'm looking, and again, I have got opposite and adjacent, so I'm still looking at tan of theta is equal to 5 divided by 9.49. So theta is equal to inverse tan of this. And the trick is, I'm solving for an angle, I'm going to be using inverse tan. If you're solving for a side, you don't have to use inverse, you're just using sine, cosine, or tan. And this gives me a value of theta is equal to 27.78 degrees. So answer number 2. All right, the last type is these sort of pyramid problems. And one of the things right away, be careful. These are not right triangles. So notice how none of the angles on any of the faces are right angle triangles. So I cannot use sine, cosine, and tangent as they are. So I need to think of creative ways to figure this out. So this question wants me to calculate the angle between the length AE and the base ABCD. So A to E is really straightforward. It's this line here. Now, one of the issues is the base ABCD is the bottom square. So for a lot of us, we might see like, oh, hey, there's a triangle here. Why don't I just use that? The issue is that when I think about the angle, it's actually going into the base. It's not running along the edge because that actually gives me a different angle. So one of the things I want to be careful of is that I don't want to just jump in and start calculating triangles with the face. So what I'm actually thinking of is I want to connect my E to my base, and to do that I'm going to go straight down. So somewhere at the bottom of the pyramid, somewhere inside of it is where I can draw my line, and then to connect, that's how I get my angle between A to E. And I'll call this point, I'll just call it X for right now. So it wants me, to calculate the angle theta, which is the same as XAE. It wants me to go into the pyramid and not along the base. But again here, I don't know most of the heights, or I don't know most of my sides. I have this triangle AEX. I have angle theta that I'm calculating. It actually gives me 10 centimeters, so I have a little bit of information, but I need either A to X or X to E. And X to E is probably the easier one to calculate. So it's not impossible. So to do this, I'm actually going to solve A to X. Because what I notice is if I come straight out, I can make myself a right angle triangle. So basically I'm going flat along the base. So then A to X would make my new triangle, so I have this sort of design. I have AXE, right angle, and then I have I'll call this point Y to X. And it seems at first like I've made kind of a silly choice because I don't know what either of those points are. But I actually do, because I know that this is a square pyramid because it gives me the base of 3 and 3. So I know that I had to go halfway to get to both of these points. So I know that this is 3 divided by 1/2, and then this is 3 divided by 1/2, or divided by 2. So both of these sides are 1.5 and this one is also 1.5. So now I have this ayx with 1.5 and 1.5. I can now solve 1.5 squared plus 1.5 squared is equal to ax squared. And this gives me a value of ax is equal to the square root of 4.5. So ax is equal to 2.121. So now I know that value, I can put it up here. So now I'm solving, I have an adjacent and I have a hypotenuse. So from my SOHCAHTOA, I'm going to be choosing cos. So cosine of my angle is equal to adjacent divided by hypotenuse, so it's 2.121 over 10. And then again, because I'm solving for an angle, I'm going to use inverse cos of this. And that's going to give me a final value, and I'm running out of space, so I'll come up here. All right, theta is equal to 77.75 degrees. Now, this should give you enough to go on. Just so you're aware, if I had calculated just using kind of this outer face, I would have gotten an angle. So if I picked A, E, and then I'll use the same point Y. So this would be 1.5, this would be 10, and this is my theta. I would get a value for cos, or for theta, of around 81 degrees. So notice how it gives me a different amount. The reason being is the face is determined by a different value than the base and the width. I'm using a different sort of dimension, or I'm using a different plane, so my angle isn't actually connected. This is where my angle starts, but it doesn't open up into the pyramid. It opens up along the edge, so it can use a different set of rules. So this should give you enough. Basically, the main takeaways are: turn this into a two-dimensional problem, be clear about your angles, don't get yourself mixed up, and make sure you're setting up your angles properly. So look for two right angle triangles that share a connected side, and that usually they're going to involve a base and they're going to involve some sort of cutting through the shape. So you want to share that sort of a side that cuts through the same plane, what we can say. So that's all for me today. This should allow you to answer those last two questions. I know they look tricky, I know they seem daunting, but in reality, they're just very obscure two-dimensional triangle questions. As always, take care, stay safe, have a good one. Next class, my next lesson, I'm going to show you a way that we can actually use this in the real world. So stay tuned for that one. Take care, have a good one.